Alright, hell yeah. Alright, so we got mechanics of materials, and we're going to revisit this problem. This problem is solved by using yield stress. So again, here's your two equations for material mechanics. This is your scale. This is your force that you're going to, tug on something. This is what you're going to visually see. This is your change in length. I mean, we could measure that too. So this is your scale, and this is your ruler. Now on this, we've already chosen an area and we've already chosen a length. So these two parameters won't change. They're givens at the start. Now, the other two parameters have subscripts. Whether you're just taking them to a design load and a design force, that's synonymous with design stress. That's why I hate these terms. Stress and strain, they sound the same and they almost sound meaningless. So I call this strength and stretch. But anyway, so you're going to have your yield. So let's put these in here. Yield strain is synonymous with yield change in length. So that's what we visibly can see. Yield stress is synonymous with yield force. So I could solve for the yield force. That's P, like what's the most force I could put on this. And this problem was real easy because if we pull it in the middle, well this part of the bar, hell, it's resisting this force, and this part of the bar is in compression and it's also resisting. Steel is the same, and unless it's in, or this doesn't say it's steel at all, but it doesn't say that there's a difference between so this is just assuming tensile stress is equal to compressive stress, and that's the property of steel. Now if this was a concrete bar, oh hell no, this problem wouldn't just be as simple as doubling this. So that's what you're basically doing. As you're pulling this part of the bar can only reach 36 psi, and it's resisting at 36,000 psi. 36,000. And this side of the bar, when it gets compressed in, can only take a pressure of 36,000 psi. That happened. That's happening basically twice. And so you're getting this force P is so if you rearrange this, your yield force is equal to 2 times that. You know what I mean? Because it's double. So it'd be 2 times sigma y times area. And we've done this problem before, and you get it's about 10,200 pounds per, so you're going to multiply by that too, and you get 20.4 thousand pounds. So now what we're going to do is we're going to change this problem around. I'm going to change this into a square bar, so that previous problem, you can look that up, I already did it. But we're gonna make this a square bar with an area of 1 inch squared. You know what I mean? And we're going to say its initial length. I'm going to actually draw another picture over here. We're going to say its initial length was 2 meters. You know what I mean? So the halfway point, we're going to have 1 meter here. Sorry to draw that line in there, and 1 meter here. Now, we're going to, instead of, this problem was like, hey, let's pre-stress it to a certain PSI in here. So this is going to be very useful because all the problems typically kind of are centered around that equation, where these two equations are the same. Because when we reach the max force, or the max per unit, per area of whatever the hell we're doing with, so this max yield stress is synonymous with, so at the point where you reach this yield, this max yield, that's when you reach the max strain. Cool. Yield strain would be be max when yield stress is max. All right, so we're gonna use this equation and make this problem make sense. So now instead of pre-stressing it to 10,000 psi, we're just going to pre-stress it visually to let's say this is 2,000 millimeters. So now we get that, and this is 1,000 millimeters, and this is 1,000 millimeters. Sorry about the and we're going to stress it 2 more millimeters. So if we have a halfway point, we're going to have 1,001 millimeters here and 1,001 millimeters here. Now this problem will make sense because we know for steel, this value, the strain, max strain, or yield strain, or you know what I mean? Yeah, we'll just leave it at that. Is 0.002. Okay, so now let's go back to the equation, because you always have this equation. Anytime you're kind of confused about strain, well, write out the whole equation. You know what I mean? So we got yield strain is equal to change in length yield divided by length. And now what do you want to find? You know what I mean? Well, let's find this value. So let's rearrange this equation, and we're going to go change in length yield is equal to yield strain times length. And it's as easy as that. We're going to put 0.002 right here, and our length is 2,000 millimeters. Okay, so we're going to get a number that's 4, and we're going to get 1, 2, 3. So we're going to get 4,000, but then 1, 2, 3. So we're going to get 4 millimeters after running this calculation. So that's why I chose just a pre-stress of 2 millimeters, because that's halfway. You know what I mean? And then so let's throw some numbers on it. I don't use this for yield steel. I mean, just as my go-to, I use the yield stress of steel, and sometimes I call it just the breaking stress. And the reason I call it breaking is it's not that it's the ultimate. It's just mentally for me is like, hey, this is when you're going to lose your job and people are going to lose their lives. You know what I mean? You don't want to get into the plastic zone unless you have a very specific application. But when you're just learning material mechanics, just know that, hell, any problem, this is a ceiling that you can always double check the problem to make sure you're hella with, under. So you can just easily see if a problem is not ludicrous just by, hey, I have a diameter of 0.6, so I'm going to go pi divided by 4 times 0.6 squared. I have an area of 0.28, so I'm just going to multiply that by 58,000, or what the hell? Force over area, and I'm gonna do 58,000 psi. I know that's the term. That's what I'm going to be using for steel. Psi multiplied by the area, so times 58,000. And I know that this can't see a force more than 16,000. I mean, if it was just a single bar, you know what I mean. If I got a single bar and I'm putting a load on it, I can't have this exceed 16,399. So even just right there, that's how you should start problems. Is like, okay, now I know this is a high end. It's a ceiling. That anything that deals with this problem, with a bar just being loaded, just from one end, the problem statement should be less than this. Else you got issues. Okay, and all right. So now we know that's our max psi, and we also know that's synonymous with the max change in length. So the max change in length, if we had a 1 meter bar with a strain of 0.002, well, let's do the equation. The change in length would be strain times length. So that would be times 1,000 millimeters, and we would get 2 millimeters. Okay, we have a 2 meter bar, 2,000 millimeters. We can stretch this thing 4 meters. Oh, now my train of thought's getting back. All right, hell yeah. So we're only stretching it halfway, and it's a linear relationship. So that's where you get this stress strain curve. Here's your 0.002, and we're just taking it to the halfway mark. So now, since it's a linear curve, hell yeah, my stress is just half of 58,000. All right, so I'm going to say this is pre-stressed to 58 divided by 2, that's 29. 29 psi, so that's going to be basically my pre-stress. Well, what do they call it? Initially, the tensile stress in the rod. Yeah, they're okay, hell yeah. And then, so now the question is, now we're going to get to the actual geometry of this problem. So when we apply a load P right here, all right, take a breath. So we stretch this out. We're going to divvy it up into two sides. This side is stretched. And if we do this, well, this side is stretched. Okay, but if we go back here, now we're going to put a load P on this side. We're going to stretch this side more. You know what I mean? It can't stretch very much more. This length, and you have to go from its original length. So this bar right here was 1 meter or 1,000 millimeters. We know from the max strain or the yield strain of steel, this can only be a change in length of 2 millimeters. So when we cover this, it's already lengthened 1 millimeter. So the second we use a force and we lengthen this 1 more millimeter, this thing is shot. And I say shot as it hit that, that ceiling where you're just like, whoa, are people going to lose their lives? Well, not in this case. If you just took it 1 millimeter, there's plenty of designs where you can take things to the limit if it is in a statically determinate, like a setup. So sure, you can put this load on. This bar hit the ceiling and now is stressed to 58,000 psi. Now what the hell is the stress in this one? Well, this one was lengthened by 1 millimeter, and now you just push that in 1 millimeter. So now this thing is back to hell yeah. It's back to original 100 millimeters. Even though that this bar is totally shot. Now it's not shot and it's not doing anything. It's not shot in the fact that it's breaking. It's just hitting its plastic limit. You know what I mean? But if you had this bar, if you put 20,000 pounds on this bar, well, it's like, oh, is it just hitting its plastic limit? Yeah, but it's physically moving and can't stop. Nothing is stopping it. It breaks and people die. You know what I mean? But in this case, no. If this hits its plastic limit, it's being backed up by this force. So it's just like, okay, like it's just there. And now let's take it. So at 1 millimeter, it's hit its plastic limit. Now let's take it another 1 millimeter. Now we're so we went 1 millimeter, 1 millimeter, and now we're right here on the chart. You know what I mean? And this is 0.2% on the chart. And if we went 25 times this, you know what I mean? Like well, I don't know. This would be, how would you do it? 1, 2, 3, 4. You know what I mean? You'd be hella over here by the time this, like steel can stretch 5%. You know what I mean? 25 times as much as this 0.2. So in that case, yeah, because this is 0, this is 0.2. We would go 3, 4, 5, 6, 7, 8, 9, 1%. That's 1%. And then you'd go another 2%, 3. So you're off the page of how far something of steel can actually stretch. So yeah, this little extra 1 millimeter is such potatoes. And so you have designed something that reached its plastic limit. It reached its ceiling, but it's still a very functional piece of, it's still holding that, in this case, 58,000 pounds. Because now I'm going to say that these are, that 1 inch square bar. Area is 1 inches squared. Cool. So that side of the bar can carry 58,000. And just know that this problem is just double that. When you put, what's the max load P force you can put on it? Well, it's just double 58,000. It's 116,000. So that problem was answered in the first time I tried to solve this. But now I'm just showing you from a change in length perspective. It's just like, cool. So let's go back to it. So we moved this 1 millimeter. This one went plastic, and this one's just happy as a clam. Now, how many millimeters can we move this one? Well, it initially was a 1 meter bar. we can make it 0.002%. And if you lose your mind and you're just like, I don't know what the strain means, hey, go back to the friggin' equation. Rearrange it and solve for what you want. I want to solve for that change in length. It's just strain times length. But I just didn't do this as an undergrad. I didn't realize this was an actual equation that you just get to use. Like, for whatever reason, the textbooks, like, hide it from you. You know what I mean? The whole concept of, like, you know what I mean? I swear to God. But anyway, so let's do it. So we have the initial length of, so we rearrange the equation. We have the initial length of 100 millimeters. Our max strain is 0.002, and we get 2 millimeters. So now that this one is happy as a clam, we can make it go 2 more millimeters. 1, 2. So we took this pre-stressed 2 meter bar, stretched it 2 millimeters. You know what I mean? Basically, one millimeter for each half. We stretched it 1 millimeter this way. This one's done. This one's neutral. And we stretch it another 2 millimeters. And now this one's done. It hit its plastic limit. So there you go. And after that, if you put more pressure or more force in this 116, sure, it just turns into Play-Doh. And even though it's in between two things, it turns into Play-Doh, and then, or it breaks compressively. Things turn into Play-Doh more when they're in tension. When they're in compression, hell, they'll just build up and probably shatter at a 45-degree angle. And we'll talk about that more in the other problems that I want to do. But anyway, so I think I did it. That was doing this problem from a change in length perspective. And it's just like, I think more problems need to be done from a change in length perspective. It's your gold standard to actually understand what's going on, especially when going back to, hell yeah, this is a spring that now is extra sprung. It used to look like this. But now you stretched it out to here, and now you're taking this point and stretching it farther. So this is like, oh, hell no. And now this one's like, I'm normal. And then you're going to stretch it even farther, and this is just like, what are you doing to me? And then finally this one gets, compressed enough where it's like it reached its limit too. So that's technically what's going on in a nutshell. That's why you have... And so this side of the bar went plastic first. If you wanted to know that, that's when this one went plastic first. And let's solve that one. Because if this was a one-star problem, it would be like, what's the force to yield? You know what I mean? And what the hell does this mean? It means how much force can you put into the system where if you let go of that force, every molecule goes back to its original shape and nothing was plastic. Well, that's an easy one. Everything was stretched out 1 millimeter. If we stretch it this way to 1 millimeter, then that went plastic. But right at that point, it's not. You know, anything more than 1 millimeter of change in length, yeah, then this part's plastic. But just 1 millimeter and then you back off. Hell yeah, every molecule went back to its location. So let's solve this problem. If it was just one bar that was 1,000... Well, let's do this. So what we're doing is we're stretching this bar 1 millimeter, and then we're compressing this bar 1 millimeter. So essentially, we're taking this material that has a area and a yield stress, and we're changing its length by 2 millimeters. And we already said that a 2 millimeter, if we just had that material, same shape, and we stretched and it was 1 meter, oh hell no. No, I'm getting, I'm going to assume these are two different bars. You know what I mean? I think that's a good thing to do. It's pre-stressed, so this 101 millimeters doesn't count. You always take its original length, because that's the concept of a spring. If you take the original length of a spring, then it has a spring constant to it. All right, hell yeah. Let's see if we can just do this mentally. So we're tensioning this one by 1 millimeter. Cool. How much pressure does that take? Well, it takes half of the max, so that took 29,000. And then we're taking this rod and we're compressing it by 1 millimeter. Cool. That also takes 29,000. So to the plastic, see the terminology is just hell. But the yield force, you know what I mean? I can put 58,000, the 29 on that one and 29 on that one, those double. So I can put 58,000 pounds as P, and then when I back off, every molecule goes back to the same location. It's within this elastic range. It hit the ceiling, but then went back down to 0. The second you go plastic, no, you permanently elongated it, whatever that was. And like I said, this is 2 millimeters of plastic. You could get up to 50 millimeters of plastic, still not have it break, let go of the tension, and it's going to go back to 48 millimeters. See, so a lot of people don't put numbers on these, and you know what I mean. If you stretch it 10 millimeters and then back it off, well, it's going to back off 2 millimeters. Now this is ideal because we chose getting into trouble. That's if I chose a 1 meter bar. You know what I mean. This bar, that's why I chose 1 meter bar on that side, 1 meter bar on that side, because we're essentially saying, hey, we got 2 springs here. We got this spring, you know what I mean, and then butted up against this spring. And then we're pre-stressing both strings so they're tensioned, and then we're saying we're moving this line. So this one's hella, and now this one's back to normal. So in this problem, the way I laid it out is yes, I'm basically treating this as 2 different lengths of bar, and I think that is a normal thing to do, and in a lot of cases you have to do that. That's why if you have something that's tapered, you almost have to just chop it up into a bunch of sections and then treat every little section as it has either a tensile. Anyway, I think I'm going to end it there. I think I did a good job of explaining change in length, or not. You know what I mean? Holy hell! But I'm pretty satisfied. That was my mission and my goal, and I think I did it. So, alright, thanks for joining me, and that's a video.